Imagine a world where machines can learn from past experiences and predict future outcomes. Welcome to the world of supervised learning. This intuitive branch of machine learning is like a teacher-student relationship. The teacher in this case is a labeled dataset, a collection of examples with known outcomes. The student? That's the algorithm, learning from the dataset to predict future outcomes. Supervised learning is a key component of artificial intelligence, enabling machines to make intelligent predictions. It's like giving the machine a crystal ball, but instead of magic, it uses data. From predicting house prices to identifying spam emails, supervised learning is the secret sauce behind many of the technological marvels we see today. It's a powerful tool shaping the future of industries from healthcare to finance. So how exactly does supervised learning work? Let's dive deeper. At the heart of supervised learning lie two main components: input features and output labels. Let's take a moment to untangle these concepts and understand their role in creating intelligent, data-driven predictions. Consider a labeled dataset as a kind of teacher, providing our machine learning algorithm with the correct answers right off the bat. This dataset is made up of examples, each consisting of an input feature, think of it as a question, and an output label, which would be the correct answer. Imagine we're training an algorithm to recognize images of cats and dogs. Each image is an input feature, and the label, cat or dog, is the output label. Our algorithm, like a diligent student, learns from these labeled examples. Now, how does this learning actually happen? The training process is where the magic of supervised learning comes into play. The algorithm sifts through the labeled data, studying the relationship between the input features and their corresponding output labels. Picture this as a complex puzzle, where the algorithm tries to decipher a pattern or a function that connects the features to the labels. Once the algorithm understands this function, it can use it to make predictions on unseen data. Going back to our cat and dog example, once trained, the algorithm could take a new unlabeled image and accurately predict whether it's a cat or a dog. This is the essence of supervised learning from labeled data to predict the outcome of new, unseen data. But the key to a successful learning process is choosing the right algorithm for your specific task. And this is where the types of supervised learning come into the picture. Now that we've grasped the basics, it's time to explore the two main types of supervised learning: regression and classification, the two superheroes of supervised learning. While they may sound like complex jargon, they're actually quite straightforward when you break them down. Let's start with regression. Imagine you're a real estate agent trying to predict the selling price of a house. You have various factors to consider: the size of the house, its location, its age, and so on. These are your input features. The selling price, a continuous value, is what you're trying to predict. This is a textbook example of a regression problem. Regression is all about predicting a continuous output value based on one or more input features. It's like trying to hit a moving target. You're not just guessing if the price is high or low, but you're estimating an actual value. Now let's move on to classification. Think of an email service provider trying to filter out spam emails. The input features could be the email text, the sender's address, the time it was sent, and so on. However, instead of predicting a continuous value, the goal here is to categorize the email into one of two classes: spam or not spam. That's what classification is all about. Categorizing inputs into distinct classes. It's a binary decision, a yes or no, a 0 or 1. So, when we talk about supervised learning, we're essentially talking about either regression or classification. The choice between the two depends on the nature of your problem. Are you predicting a continuous value, or are you categorizing inputs? And remember, these aren't just theoretical concepts. They're being used every day to make our lives easier. Whether it's predicting stock prices, detecting spam emails, diagnosing diseases, or even recognizing speech, regression and classification are at the heart of these intelligent predictions. So, which algorithms power these supervised learning tasks? Let's find out. Meet linear and logistic regression, two key players in the supervised learning arena. Let's start with linear regression. As a cornerstone of predictive analytics, linear regression is all about finding the relationship between two variables. Think of it like this. You have a set of data points and you're trying to fit them into a straight line. This line is the best fit because it minimizes the distance between itself and all the data points. Linear regression is perfect for predicting numeric values. For example, it can forecast sales based on past trends or predict a house's price from its size and location. Now let's move on to logistic regression. Despite its name, it's not a regression algorithm, but a classification one. Logistic regression estimates the probability that a given input point belongs to a certain class. Instead of straight lines, it uses the logistic function to squeeze the output between 0 and 1. This makes it ideal for binary classification tasks like determining whether an email is spam or not spam, or if a tumor is malignant or benign. Imagine you're trying to predict if it will rain tomorrow. Linear regression might give you a value like 1.2, which doesn't make much sense in this context, but logistic regression, it'll give you a probability like there's a 70% chance of rain. Much more useful, right? But here's the catch. Both linear and logistic regression assume a certain structure in your data. Linear regression assumes a linear relationship between input and output, while logistic regression assumes that the log odds of your output can be expressed as a linear combination of your input variables. If these assumptions don't hold, your model's predictions might be off. One more thing. While linear regression is quite sensitive to outliers, logistic regression is more robust. So, if your data is plagued with outliers, logistic regression might be a better choice. But how do we measure the performance of these algorithms? Enter evaluation metrics. How well does our machine learn? Evaluation metrics have the answer. Let's start with regression problems. Here we often use the mean squared error, or MSE. It measures the average squared difference between the predicted and actual values. A lower MSE indicates a better fit model. Now let's turn to classification tasks. Here we have a suite of metrics at our disposal. Accuracy tells us the proportion of correct predictions. Precision is the ratio of true positives to the sum of true and false positives. Recall, also known as sensitivity, calculates the ratio of true positives to the sum of true positives and false negatives. And the F1 score? It's the harmonic mean of precision and recall, giving us a balanced measure of the model's performance. With these metrics, we can optimize our models for the best performance. But where do we see supervised learning in action? From medical diagnosis to financial forecasting, supervised learning is everywhere. Let's take a journey around its real-world applications. In the medical field, it's a game changer for disease diagnosis. By training on historical patient data, algorithms can predict potential health risks, improving prevention and treatment plans. Now let's talk finance. Stock market forecasting, credit scoring, supervised learning has got it covered. By analyzing past financial data, it can predict future trends, helping investors make informed decisions. Let's not forget natural language processing. Sentiment analysis, for instance, uses supervised learning to classify text into positive, negative, or neutral sentiments. It's a vital tool for companies wanting to understand customer feedback. From healthcare and finance to language processing, supervised learning is revolutionizing industries with its predictive power. It's not just about understanding the theory, it's about seeing it in action. From theory to practice, supervised learning proves to be a versatile and powerful tool in the realm of machine learning. As we wrap up, let's revisit the key takeaways from our journey into supervised learning. We've delved into the inner workings of this fundamental pillar of machine learning, exploring its core concepts, types, and applications. We've seen how supervised learning, with its labeled datasets and predictive powers, serves as a cornerstone for intelligent data-driven predictions. We've also looked at the different types of supervised learning, including regression for continuous predictions and classification for discrete categories. We've explored key evaluation metrics and their role in determining the performance of our models. We've seen supervised learning at work in real-world applications, from medical diagnosis to financial forecasting and language processing. It's clear that the impact of supervised learning is far-reaching and transformative. So here's my challenge to you. Dive deeper, explore further. Apply these concepts in your own projects and see what you can achieve. With supervised learning, the possibilities are endless, so go forth and let your machines learn.